So next we're just going to apply those definitions of divergence and curl to finish a problem. So given this vector field, f equal to x squared y z x, we'd like to compute the divergence and the curl. So from our formula, divergence is given by dA dx plus dB dy plus dC dz. And if you wanted to write that as a dot product to get to this point, that's fine. So for the particular f we have, our a, b, and c components are just those first, second, and third entries of f. So we're going to be taking d dx of the first component, which is x squared, then d dy of the second component, which is yz, and then d dz of the last component, which is just x. So d dx of x squared, that's going to give us 2x. And then d dy of yz is just going to give us z. And then d dz of x is actually just going to give us 0. And maybe you just want to leave that off entirely because it doesn't do anything, the plus 0. So just to be clear, when you're taking those partial derivatives, you need to make sure to keep the partials of all the components separate from each other. And then this would be the answer for the divergence. To compute the curl, if you're more comfortable with it, you could go ahead and just plug in ABC to this formula right here and evaluate all your partial derivatives and simplify. But I'm going to show working it out the determinant way because that's something that some people are comfortable with. So when you do the determinant cross product, I know it's been a while, but we put I hat, j hat, k hat in the top component, and then entries of the first vector in the middle and the last vector down below. So the gradient vector is our, sorry, not gradient, del operator is our middle vector. So we've got d dx, d dy, and d dz right there. And then we would put the entries of f, a, b, and c right here. So for us, our entries of a, b, and c we know are x squared, y, z, and x. And then the way you compute the gradient is you look at I hat first and then take the determinant of the entries that aren't below I hat. So that's going to be d over dy times x, and then minus d over dz times yz. And then next you move on to the j hat component, but we always go in determinants plus, minus, plus as we move from left to right. And so this is going to be minus whatever we get from the j hat. And in this case, we ignore what's below j, and then we do d dx times x minus d dz times x squared. So we're going to get like that. And then we move on, adding the k component. We're going to ignore what's below k, and we'll have d dx of yz minus d dy of x squared. So that's going to be d dx of yz minus d dy of x squared. And then we go ahead and compute all these partial derivatives and start to simplify it. So d dy of x is 0, minus d dz of yz is just going to be y, right there. And then d dx of x is just going to give me 1, minus d dz of x squared, again that's 0. So I know it's been a while since we thought so much about partial derivatives, but all the other variables with respect to z are going to be considered constants. That's why I get that 0 out of it. And then d dx of yz, for the same reason, is just going to give me another 0. And d dy of x squared, again, gets me 0. because there's no y to contribute to that derivative. And so simplifying all that, I just have minus y I hat minus j hat and no k hat. And if I wanted to write that as a vector, it would be minus y minus 1, 0. So that's how we apply the definitions of divergence and curl to a vector field. And I know this seems like just another sort of random definition that we got. We're going to end up using these definitions when we learn special properties of integrals moving forward. But for now, it's just sort of some groundwork we need to work with this new type of mathematical object. One thing that I do want you to be careful about is to note that divergence up here gave us a scalar value. So it wasn't a vector. It doesn't have I hat, j hat, k hat components. It's just a regular number or regular variables. And then curl, when we computed it down here, was a vector. So if you ever try to take divergence and get a vector, you know something went wrong. If you ever take curl and get a bunch of scalars, you know something went wrong. Same as with dot product and cross product, because that's where they come from. And then the only thing that's different about this from when we learned how to just take regular dot and cross products is that the components of the divergence and the curl can be functions of x, y, and z. So you don't need one single number at the end. You can have something that depends on x, y, and z. But it doesn't necessarily have to always have variables in it. So in that curl we did, we got minus 1 and 0. Those are just numbers. Numbers are functions of variables. They're just very boring functions. So we also need to learn a little bit of vocabulary about vector fields. So we finished that example up above. And I just want to note this new definition we have, which is that a conservative vector field is a particular type of vector field that is path independent, or the other word you'll hear about this is that it's irrotational. And we'll work more with this idea. It's going to be a special condition we need for certain integral rules to apply. But just so that you can sort of build a physical intuition for what a conservative vector field is, I want to talk about gravity. So gravity is a vector field. It has magnitude and direction everywhere. The direction is pulling you down towards the ground, and the magnitude is whatever your gravitational constant is. And so that particular vector field is independent of position, or the path you take. So kind of if you imagine taking an object, like you're sitting down and you throw it across the room, the gravity that object experiences falling down to the ground is the same as if you took that object and just dropped it from the same height. Sort of its vertical and horizontal motion are different, and that horizontal motion doesn't affect how gravity influences the object. So that's sort of the most classic example of a conservative vector field that you might be familiar with from other classes. Mathematically, the way that we're going to identify conservative vector fields is that if F is conservative, there are sort of two properties that we'll rely on. So the first is that the curl of a vector field is going to be 0. You can always go ahead and test that. If curl F equals 0, F is a conservative vector field. And then also, you'll be able to say that F is equal to grad little f for something that we call a potential function, F. And today, we're going to work on examples that help us find out what a potential function for a vector field is. We won't really work with this definition right here, curl f equal to 0, you already know how to compute the curl. Checking if something is conservative would just mean computing that curl and seeing if it's 0.